Hello everyone. I hope you are all doing well and staying safe. In this video, we will discuss practice assignment 10. Um, we will have a recap first on the data path we have discussed last tutorial, and then we will have um, an introduction to pipelining, and then see some problems about or exercises about pipelining. If you don't understand the data path, you can either start reviewing with us in this tutorial, or if not, then go and watch first the last tutorial 9, and after that come back to watch this video. Okay. I hope you understand, and if you have any questions regarding this or the revision before this video, please send us an email or whatever you want to how to communicate with us. So let's have a look on this data path we are having here. Like we said before, we are having 5 stages, and we will have a quick revision on each stage of them. And here is the data path. We are having the data flowed in this drawing. We start with the PC, setting the address for the next instruction, and we are having the instruction memory where all the instructions are saved, and then we have the register file where we are having the registers, and we have the LU where we execute or we perform the main operation of our instruction, and we're having at the end the memory where the data is stored. This is the data memory, not the instruction memory, and we have seen the difference before, that the instruction memory contains the instructions only, while the data memory contains the data, not the instructions. Okay, and we access it using load and store only. um, and the final thing is that we write back to the register file if we are writing something to the registers, as in the addition, subtraction, load, or any instruction that wants to write in one of the registers. Okay. The first stage is the fetch stage, where um, we know now um, we know now that it takes the address from the PC. What address? The address of the instruction we will implement. Okay, and then it goes to the instruction memory and go to this address, fetch the instruction. What does fetch means? It means that we take the 32 bits that represents this instruction and move it with the data path to the next stage. So the stage here is in red, and this is very important because it mainly after that we extract the first 6 bits, which are the opcode. And as we see here to the right, we have the 3 different instruction types, R, I, and J, and we will classify the instruction or categorize the instruction according to those types with the opcode. Okay, so this is the fetch stage, and it contains no control signals. Then we move to the second stage, which is the decode stage, and it's highlighted in red here, or in the red rectangle. This is the biggest part in operations, not in time. So it takes not long time, but it contains many operations. The first operation is dividing the instruction according to its type. So we first check the type of the instruction according to the opcode, and then divide it according to the instruction types we are having to the right. So it's either I, J, or R, and afterwards we take those inputs and divisions and use them. So for example, here, as I have in this figure, the instruction from 25 to 21 is considered RS, so it's considered read register 1, and I enter the register file, take the data from the register file, and uses the data in the data path in the next stages. Okay, and so on. So In the decode stage, two main things happen, dividing or more than two things, but the two important things maybe are dividing the instruction and having the control unit. What is the control unit? The control unit, we don't, where it's not visualized here in the graph, but it's a black box where we give this black box what the opcode, the 6 bits opcode, and according to this opcode, the it translated into or converts it into something called control signals. What are the control signals? They are the signals or the bits we are having here in light blue in the data path. So, for example, reg write, register destination, mem read, PC source, and so on. And these bits are 1 bit only, so it's either 0 or 1. It's either do this or do that. So, for example, the mux we are having in any of them, if reg destination, which is the very first one, near the register file, if it's 0, it will pass what? It will pass the first port, which is instruction from 20 to 16. If it's 1, it will pass the second half, which is instruction from 15 to 11, and so on. So these control signals are responsible for deciding for me what, or for the data pass or this instruction, what it should do and what it can't do. Okay. And we explained that in the last tutorial, but this is just a brief. Okay, so what else does this stage contains? It contains the sign extend, which we mentioned last time, and it contains also retrieving the data from the registers, which is very important, of course. And as we said before, the register file is like an array of registers, so it's an array containing many registers. How many? There are 32. And we have seen in the last two tutorials what are the registers we are having and the options we have. Okay. The third stage is also very important, since this stage uh, is a stage where any operation can happen here. Okay, so any comparison should happen here, any addition, any subtraction, whatever we are doing in our instruction should be done here. So what are the inputs for this stage? We are having the read data 1, which is the RS in any of the instructions, and we are having a second input, which can either be the second register or the immediate value. Okay, and we do here the operations that we want to do. So it's either addition, subtraction, multiplication, load, store, whatever we are having. And how we do the load and store, since we are still not in the memory stage, we just here responsible for adding the addresses. How we do that? We add the base address with the offset we mentioned in the last lab and tutorial. Okay. So it's mainly doing whatever this operation or instruction wants, and um, it's very important to know how we do that. You see here the ALU control. This is an input to the ALU. So these are whatever bits we are having. If you are having, for example, 4 bits, then I can represent how many instructions or how many operations in my ALU 2 power 4, which is 16. So I can have 16 different operations: addition, subtraction, shifting left, shifting right, whatever the options we are having. So that's how the ALU knows the instruction it will implement. Okay, and of course it's controlled by the control unit, which generates what? Um, the blue and signals we said before, called control signals. The fourth stage is also important, but in a different way. Why? This is the data memory where all the data I have is stored. Okay, so this memory, since it has all the data, then I should access it little time, not always. Why? As we mentioned before, that accessing the memory causes much delay. So that's why in this stage is the slowest stage, causing much delay for our data path or our implementation. And that's why we have only two types of instructions that can access this data memory. What are them? Yes, as we said before, it's the load and the store. So load word, load byte, store byte, and we mentioned different types of loads and stores before. We are having only two instructions that can access the memory. It can be done using one of the two instructions. The first is load. How can I load? I load from the memory, so I take data from the memory and put it into one of my registers. This is the load, and the store is the total opposite. So I have data in a register, and I want to store it in the memory. Okay, so you should understand the difference between store and load, because sometimes things get mixed. Okay, and you can see also in the red box we are having here two control signals. What are them? Mem write and mem read. Mem write is responsible to be 1 whenever I am writing to the memory, which is in what? In store. So it only be 1 when I am in store. And mem read, of course, I'm reading from the memory and taking these data to the register. Then I'm doing what? I am reading from the memory. So mem read will be 1 in case of load only. And of course, they can't be one together, since I'm either loading or either storing, or I'm not using the memory at all. So both of them will be considered zeros. And the final stage is highlighted in red as well, which is the write back stage, where we choose between writing from the memory, getting the input from the memory, or from the ALU, and after that we write to the registers, put the output in the registers. Okay, this is the final port of our data path. So we are having now 5 stages. Each one of them waits till the other um, completes totally. So the write back waits for the memory, and memory waits for the execute stage, and the execute stage waits for the decode stage, and the decode stage, of course, waits for the fetch stage. Okay, and we have here each instruction. Whenever each instruction finishes, the next instruction starts the 5 cycles. So all what we have discussed in the revision of this tutorial or in last tutorial was what? Single cycle data path. What is single cycle? It is that each instruction finishes, and then the next instruction starts, and each instruction waits for the instruction before it to finish in order to start um, implementation. Okay, so what we want to discuss now is something called pipelining. What is pipelining? Is that we want that instructions work at the same time. Okay, so instructions work at the same time. Let's have an example first about the concept of pipelining in general, and then apply this concept or apply this example on um, what we are having in computer architecture. So in the example here, we are having in this picture, we're having the pipeline way of Subway. The restaurant called Subway. Okay, so how they do it? They have a guy standing on the bread type, and a guy on the type of cheese, and if you want to toast it or not, and then what type of meat you want, chicken or beef or tuna or whatever chicken you want, and then the vegetables you want, and then the sauce, and then if you wanted a meal or just a sandwich. Okay, so um, that is the pipelining they are having there. Okay, imagine we are having 10 customers, and each customer is waiting for the the customer before him, okay? And what should the guy do? He should wait for um, he should wait for um, the one previous to him or before him to do the whole thing and have the sandwich and pay, okay, and then start this thing all over again, okay. So each one will wait for like seven stages, and then the guy another one, so the last one in the line will wait for how much time. If it takes 10 minutes for example to do one sandwich, and then he will take 70 minutes, okay. So they did a nice solution, which is having a guy on each of these stages, and that um, customers go from one stage to another. So the first guy is on the bread, so the rest are waiting, and then this guy moves to choosing the cheese. The second guy will go and choose the bread, and so on, as we see here. So the first guy in the dark green, okay, will finish first. This is the normal, but the second person in light green, instead of waiting for this person to finish totally, he will wait only one stage, so he will have only 1 minute delay more than the guy before him, not 7 or 10 minutes delay, okay. So this is the concept we will have in our MIPS implementation. So instead of implementing or waiting for the instruction before me to finish totally, okay, I will do what? I will enter um, I will enter the data path after some sort of delay. Why after some sort of delay? Okay, in a perfect case, ideally, I want all the instruction. If I have 10 instructions, I want all of them to run at the same time and finish at the same time in a very short time. But this is not applicable. Why not applicable? Because, for example, if I'm having two instructions at this, the 10 instructions, for example, at the fetch stage, which one will take the address of the instruction? I won't know, because all of them needs to use the instruction memory at the same time, which is a problem, a huge problem, because hardware cannot serve more than one instruction at one time, okay. So that's why I won't be able to do the pipelining in a perfect case. So I have to wait for the first instruction to finish fetching, so I can fetch the next instruction, and then I wait for the second instruction to fetch, and after that I will fetch the third instruction. So as we know, we're having 5 stages: fetch, decode, execute, memory, and write back. Okay, so since we are having those 5 stages as we mentioned, what will we do? We will wait for each stage to finish, and then the next instruction will be with us. So if I am having 5 instructions, the first should be at the write back, the second at the memory, the third at the execute, the fourth at the decode, and the fifth at the fetch stage, and so on. We will have several examples to understand that, but this is the main concept of pipelining: to have everything in parallel with a slight delay, so that not all the instruction will have to access the same hardware at the same time. So let's have our first question. Consider the following stages latencies, and each one is having its certain latency. So we have fetch, decode, execute, memory, and write back. What is the frequency of this processor in case of single cycle implementation, and what we have the frequency for the processor in case of pipeline implementation? So we had this question in last tutorial, but we did it in only single cycle. How did we manage to do this? Is that we first we have first searched for the slowest instruction, so to know the longest time for this single cycle, which was 800 picoseconds. Okay, how we did that? We added the 5 stages together, and the frequency was 1 over this time, which was 1.25 gigahertz. So the difference between the pipelining and the single cycle is that the single cycle have all the 5 stages are done in one cycle. Okay, in the we should have all of them in order for the next instruction to come in and start its implementation. So that's the frequency for the single cycle. For the pipeline version, it's a little bit different. Why? Because the next instruction or the second instruction doesn't wait for the whole instruction to finish, the whole instruction before it to finish. It only waits for what? For one stage only. Okay, so as we see here in the graph in front of us, we are having the blue instruction at the beginning, and then after it finishes the 5th stage, the next instruction appears, which is the 5 stages, the 5 stages, the 5 stages of the second instruction in red. Okay, so that's why we are having 2 instructions. Okay, and in the other one, in the pipeline version, it's totally different. Why? Because the second instruction entered in the second stage time. Okay, that's why if I want to evaluate a stage time or a clock cycle time, I have to get only one stage. But which stage from the 5? The slowest one. Why? Because for example, here I have the decode taking 100 seconds, and I have the fetch taking 200 seconds. If I only reserve it 100 picoseconds, okay, for the fetch, it won't be able to finish, so it won't do the job we want, and that's why we will have to wait for the longest one. So the difference between the pipelining and single cycle is that the single cycle, all the 5 stages are done in one cycle. So each instruction has to wait for the previous instruction to finish before it starts. However, in pipelining, instruction happen in parallel, as we mentioned before. So the second instruction started in its fetching stage 1 instruction, and started the decoding. Okay, so the first instruction was in the decode stage, and the second instruction is in the fetch, and so on. So in the pipelining, the cycle time is the slowest stage, which is 200 picoseconds. As we see, the fetch is 200, decode 100, execution 200, memory 200, and write back 100 picoseconds. So the slowest one is 200, and as we know, we got the slowest one. Okay, and how to get the frequency? It's 1 over this time, so it's 1 over 200 picoseconds, which is a better frequency than, of course, the one with the single cycled MIPS implementation. Okay, so to summarize, these figures can show that easily. We're having here all stage time for the 5 stages, the summation of the 5 stages. While in the pipeline version, we are having the slowest one only, which is here 800, and the other one is 200, which is very big gap between them. Let's move to our next question. Draw the execution of the following instructions for single cycle and pipelined implementation. We assume the write to the registers occurs in the first half of the clock cycle, and the read from the register file occurs in the second half. Okay, we are having load S1 200 of S0, load S2 from 200 of S0, and load S3 from 300 of S0. So And let's understand the question first. In this question, we have a program containing 3 instructions, and we will see how this program will be executed in both single cycle and pipeline implementation. First, we will start with the single cycle. All stages of the instruction happen in one cycle, which takes, as we said before, 800 picoseconds. If we take, of course, the numbers from our last exercise. On the other hand, this is what happens in the pipeline implementation instruction in parallel, and we will see in the next slide how to draw them. So as we see here in the drawings, we're having the single cycle, and in this single cycle we wait until the 5 stages finishes, and then we go to the next instruction and so on. So this is the drawing, and for the pipelines, of course it's different. So what we do is that we wait for only one stage. So the next instruction fetches when the first instruction is at the decode stage, but we should note here a different thing that we haven't discussed before, is that in parallel, when instructions happen in parallel, at the decode stage, as we see, the second half of the clock is only for reading from the register, while the first half of the clock cycle is used for writing to the register. So the write back, okay, which is both of them are circled in red, and the write back, the first stage is used and the second stage is not used, while in the decode stage, which is at the beginning, the first half of the clock cycle is not used, while the second one is only used because we are reading from the register file, as we know the difference between of course the decode stage, where we read the data from the register file, while at the write back we write the data to the register file. So for the previous 3 instructions we discussed, we want to know by how much did pipelining improve the performance. What would happen if 1 million instructions are added in the pipeline example instead of only 3 instructions? So think first and let's discuss this question. So in order to compare to implementations, we should know how much time does each of them consumes or takes. So the total number in single cycle is, as we see here in the solution, is 2,400 picoseconds. How we got that question, that answer? It's 800 multiplied by 3. Okay, why? Because one instruction takes 800 picoseconds. So if we are having 3 instructions, we should multiply them together. Okay, this is easy. And while in the pipeline version, if you see the graph in the last slide, you will know that it takes 7 stages, and we know that each stage contains takes how much time? 200 picoseconds. So 7 multiplied by 200, so it takes 1,400 picoseconds. Okay, this is the difference. So if we know by how much the speed up happened in the pipeline version, we should divide 1,400 by 2,400. Okay, and we know the speed up. Okay, let's move to the second part of our question. What is the second part? Is if we what will happen if we added 1 million instruction instead of 3 instructions only? Okay, it will lead even better throughput. Why? For the single cycle, we will add 1 million multiplied by 800, as we see here, plus the 2,400 we know for the 3 instructions. So it will be 800,000 millions, and the number we are seeing here, we shouldn't care about those details. And for the pipeline version, we are having million instructions, okay, and multiplied by how much? Multiplied by 200, since each new instruction takes only 200 stages plus the 3 instructions we had before, and it will cause 200 million picoseconds. And if we compute the ratio, it will be a very big ratio. Why? Because as we increase the number of instructions, we will of course visualize or notice the big difference in time. So pipelining shows its effect, or its effect is shown in large number of instructions more than small number of instructions. And you can do the tracing by yourself like we did in the previous example, and take for example only 3 instructions, and the other one is 10 instruction instead of course 1 million instruction, and you will see the huge difference in time. And as you increase the number of instructions, this gap or the difference will appear more. That's all for this video and this tutorial. If you have any questions regarding pipelining and pipelining stages and the difference between single cycled and pipeline version of MIPS, please don't hesitate to contact me or Dr. Nada. Thank you, and see you in the next video.